Okay, good morning, good afternoon, everyone. So today we are covering NP completeness, and specifically within NP completeness, we are covering the equivalence of language and problem. This is a concept that sometimes confuses some students, so I thought let's make a short video on it, okay? Within the course, you'll find this topic right inside the analysis portion, the NP completeness portion, usually covered after we have covered all the algorithm design techniques. And the textbook follows the same pattern. So let's dive into it. So the class P and class NP are the two famous complexity classes. A complexity class is defined usually as a set of problems that can be solved within a certain usage of given resource, time and space being two most common resources. There can be others as well, though. These two classes are formally defined as, the class P is defined as a set of languages that are accepted by a deterministic Turing machine in polynomial time. And NP is defined as a set of languages accepted by a non-deterministic Turing machine, also in polynomial time. And formally, they're defined as sets of languages. Now, what does that refer to? Language is not related to a programming language as we might use in context of Java, Python, etc. Wikipedia definition is that a formal language consists of words whose letters are taken from an alphabet, and they are well formed according to a specific set of rules. So essentially, a language is defined as a set of strings and a subset of strings compared to the overall alphabet that can be the set of strings that can be constructed from that alphabet. So let's suppose we have an alphabet such as the 3 characters only. Alphabet is A, B, C. Then the set of all possible languages is denoted as sigma star. And language is a subset of sigma star. And by its definition, the language L and its complement, L prime, together will give you sigma star. So essentially, when we say a language in this context, we are referring to a language of this nature, which is accepted by a Turing machine. Now, when we use the informal word problem, we are usually referring to something that we're trying to find or solve, or at least confirm something in the sense of a decision version of the problem. For example, we could be given a graph, and does it have a Hamiltonian cycle? That's a question we would like to answer in yes or no terms, right? Let's take another example. Let's suppose we have this world capitals problem. So we would like to say, okay, we're given a set of country and city, and we would like to either say yes to it or say no to it, assuming that's right or wrong. So for example, if you're given the pair Germany, Berlin, we would say this is one episode or one problem instance, and we would like to accept it. And if we're given something else, we might reject it. For example, if we're given the pair Nepal, Thimphu, we would say no. If we would say Canada, Toronto, we would say no. And if we're given France, Paris, we would say yes. So if we were to craft the same exact problem in terms of a language, a formal language, we would say that if we are given this string, Nepal, Thimphu, we would say no to that string, or in other words, we would reject that string. Similarly, if we're given a string such as Canada, Toronto, we would say no, or we would reject that string. If we're given France, Paris, we would say yes, or in other words, we would accept the string. So this is the way we can connect problems to languages. A problem instance can be encoded as a string. For example, if you're talking about a graph problem, we can say the graph can be encoded in terms of a string where we say the first line denotes the set of nodes, the second line denotes this, etc., etc. Just like here, we would say that this string denotes is formatted as such that we have these curly braces, then we have the country name, then we have colon, and then we have the city name. So this is a little formatting of the string. And once we are given the string, we can parse it, we can check it against our database, and then accept or reject it. So that's how we would accept or reject these particular strings against our target database of the world capitals. So if the algorithm accepts an input, we say the input is in the machine, is in the language of the Turing machine, and otherwise it's not. So essentially, this is the way that we say that languages are essentially problems. A language L is a mathematical way of representing what we usually informally define as the word problem. A problem instance is equivalent to a string. Accepting a language is equivalent to solving that corresponding problem. Again, as a bottom line, language L is a mathematical representation of our informal term problem. I hope this has been helpful, but while we're on this topic, we can also talk a little bit about some of the languages that are solvable, problems that are solvable, and some that are not. So going back to the classes P and NP, the class P is a set of languages accepted by a deterministic Turing machine polynomial time, NP by a non-deterministic Turing machine polynomial time. Now they are defined as sets of languages, but by now, as we know, these are also the classes of problems. Now, technically, the N stands for non-deterministic, but it turns out that not polynomial is coincidentally a good articulation also in this case. So sometimes people will say P is polynomial and P is not polynomial. It's not strictly true, but in this case, it does turn out to be coincidentally a good articulation. Okay. Let's talk a little bit about solvable and unsolvable problems. In the theory of computation, languages can be categorized in the following way. We can say there are some problems that are solvable. They're called recursive, also called Turing decidable. And now this concept recursive is not the same thing as saying recursion in Java or recursion in C, etc. Not necessarily the same. But what we are saying is the word recursive when we're using here is to say that this is Turing decidable problem. So a language or a problem is Turing decidable, so we call it to be recursive. There's a slightly weaker version to say that a language is recursively enumerable, an RE language, in which case we do accept it in finite steps, but when we reject it, we do not reject it in finite steps. The machine may go on forever. It may reject it in some finite steps, but it may also go on forever. So in that sense, the problem may be recursively enumerable, but not recursive. And finally, there are problems that are not recursively enumerable at all. So essentially, the bottom line is that there's some problems that are not solvable at all, irrespective of the time and space present. A good example of that is the halting problem. Another example is the PCP, the post-correspondence problem. And they are examples of problems that are not solvable. Hopefully, this is all helpful, and keep learning.